So before we start with this topic of lossy dielectrics, I just want to go back, to the concept of dielectrics that we have learned in our lecture in chapter 5, in chapter 5, in which for that particular case, we are considering that the dielectrics that we have are just a type of lossless medium, lossless medium, in which we can see that, um, the sigma is equal to 0. This is for the case of lossless, lossless dielectrics or perfect dielectrics, I can say. Okay, so for the case of lossless dielectric, it can be said that the sigma, which is the conductivity of the dielectric, is equal to 0. So it means that it does not incur any losses, because basically the conductivity, the sigma will actually contribute to the loss of the dielectrics. Okay, so if we have a case of lossless dielectric or perfect dielectric, it can be said that the sigma will be 0. Okay, and this is for the case of, I can say that this is not the actual case or the real case, because for a real case or real scenario, the real application, there is no such case where we're going to have the sigma is 0, for the case of dielectrics. So this is what we're going to cover, the topics which is on the lossy dielectrics, the dielectric, in which for the particular case of lossy dielectrics, can be said that the sigma is not equal to 0. So that are the things to learn in our lecture today. Okay, so to start the topics or lectures on lossy dielectrics, I think it's good if we can go back to this equation of Maxwell's, that we have learned last Tuesday, which is the Maxwell's equation in time varying field, modification of the curl of H equals to J. Previously, we have learned in static field, but for the time varying field, it is curl of H equals to J plus dd over dt, in which we have agreed in our class last Tuesday that J basically is your conduction current, is your conduction current, whereas the dd or dt here will be your displacement current. Okay, so we have agreed this symbol, I mean this case, last Tuesday. Okay, so as I mentioned now, for the case of perfect dielectric, which is for the case of lossless or non-conducting dielectrics, we have the case where sigma is 0, and knowing that for the conduction current, where we have JC, you can see the JC, C stand for the conduction. For the conduction current density, JC equals to sigma of E. Okay, so we have agreed this, in our lectures on chapter 5. So when sigma is 0, so basically the J or the JC will be 0. Okay, so this is our findings. So we have agreed on this, whereas this is for the case where we have the dielectrics to be perfect or lossless. But when we have a case of lossy dielectrics, lossy dielectrics, as I mentioned just now, whereby the sigma is not 0, so as such, the conduction current is also not 0. So we have this case. So we're going to actually distinguish, I mean, we're going to characterize what is the important characteristics for the case of lossy dielectrics. Because we know that for the lossless case, for lossless dielectric or for perfect dielectric, the dielectric is said to be no loss. It's perfect, so no loss. So it means that if we have for example, if these are dielectrics, if we have, for example, the current, for instance, we have the energy, the signal, the wave, for example, the wave propagating inside the dielectrics, which is the case to be a perfect dielectric. Sigma is 0. This is our dielectric with the permittivity of epsilon. So let's say we have a wave propagating inside the dielectric. Let's say the wave is having a magnitude, for example, magnitude of A0, for instance. So if we are having the case of this dielectrics, so at the output of dielectric, we're going to have the same wave with the same magnitude, which is A0. It means that there should be no loss. There should be no loss. So the signals or the wave propagating the dielectrics, there should be no such loss happens to this wave, and as a result, we're going to have the wave which is not reduced in terms of the magnitude. Yeah, because basically when you have a lossy medium, yeah, lossy medium here, so the magnitude of the wave will be reduced, yeah, due to the nature of the medium. But when we have a case of loss dielectric or perfect dielectric, there is no reduction, there is no loss, yeah, there is no, I can say, reduction of the energy of wave, yeah. So that should be the case, yeah, when we have a perfect dielectric. But when we have a lossy medium, what will happen? Okay, so that we're going to discuss about this issue, starting this equation here. Okay, so this is the equation related to the loss dielectric. Which we have agreed that for the case of lossless medium, yeah, we have a curl of right and the dt. Okay, so this is the equation. Yeah, this is the equation that we have learned in our class last Tuesday. Okay, where we consider the case of lossless medium, and as such, the j will be 0. Okay, and we then have these equations only. Okay, and in a phasor form, yeah, in a phasor form, we can write the d over dt here to be equals to j omega. Okay, I believe that you have learned this in signal system, yeah, last semester or previous semesters, that this is in time domain. So phasor form is basically in frequency domain, in which if we can refer back to the Fourier transform, when we have a differentiation d over dt, the Fourier transform will be j omega. Yeah, so you can refer back to our notes, to the lectures on signal system. So that's why when we have this particular d over dt, or differentiation of time for the E field, so in the phasor form, it will be j omega. So as such, you're going to have j omega epsilon of E field. Okay, so that's how we obtain these equations here, yeah, in terms of the phasor form. Okay, so this is the equation that we have in the case of lossless dielectric or perfect dielectrics. So what we're going to do now is that we're going to compare, yeah, we're going to compare the permittivity, yeah, the permittivity in lossless dielectric and lossy dielectrics. So as such, we're going to use the equation number 1, which is for the case of lossy dielectrics, this equation, yeah. Yeah, so we're going to have these equations here, yeah, curl of H equals to J plus J omega D. Sorry, I think not this one, yeah. This is actually one from the above equations, yeah, from these equations, yeah. Okay, so we have the equations of curl of H equals to J plus J omega D, yeah, and we can write J as sigma of E, which is for the conduction current, and J omega is now returned to be, yeah, J omega D is now returned to be J omega epsilon prime of E field. Okay, the reason why I'm using epsilon prime here is that I want to differentiate this epsilon prime and epsilon here. Yeah, epsilon for the lossless medium and lossy medium. Yeah, so we're going to differentiate these two permittivities. So that's why I'm using a prime sign for this particular case. Okay, so we can group this together and we can take out the E field from this equation, and as such, you're going to have, for the case of lossy medium, yeah, the equations for the Maxwell, this equation will become curl of H equals to sigma plus j omega epsilon prime multiplied with the E field. So what we're going to do now is that we're going to compare. Yeah, we're going to compare the equation for the lossless medium, yeah, for the case of perfect dielectric, and the equation for the lossy medium or lossy dielectric. So we're going to compare these two equations. So when we compare these two equations, we're going to have this. Yeah, we're going to have these equations here, where we have j omega epsilon equals to sigma plus j omega epsilon prime. Okay, bear in mind that this is for the case of perfect, okay, perfect dielectrics, and this is for the case of lossy dielectrics. Yeah, so we have these two terms. Yeah, left hand side is for perfect, right hand side is for lossy medium. Okay, so that since we want to find the difference between permittivity in a perfect medium and also in a lossy medium, so we can then simplify the equations here. So we can divide both sides with j omega. Okay, j omega. So we're going to have epsilon only on left hand side, and right hand side we're going to have epsilon prime plus sigma over j omega. Okay, so what we can deduce from here, yeah, so this is the same, yeah, we just change the positive sign to negative sign. So what we can deduce from here is that for the case of a lossless, yeah, for the case of lossless, we can write here, yeah, for the case of lossless dielectric or perfect dielectric, your permittivity is the real value, yeah, permittivity is equals to epsilon naught multiplied with an R only, yeah, this is for the case of lossless medium, which shows that for the case of a perfect medium, permittivity is real number. But when we consider the case of lossy medium, and evidently it shows from this equation, we are going to have a complex number for the dielectrics. Yeah, in which if you can write here, you can have that the epsilon for the case of lossy medium will be equals to epsilon. So I just put epsilon prime here, okay, plus j of epsilon double prime. Okay, which is we can say that for the case of lossy medium, the permittivity will consist of a real value of your permittivity, yeah, and then going to have the imaginary value of the permittivity. Okay, right? So we can see the difference between the permittivity for a lossless medium and permittivity for the lossy medium. And I just want to stress one more time that for a lossless medium or lossy dielectric, permittivity is real number. But for the case of lossy dielectrics, permittivity is a complex number which consists of real and imaginary. Okay, what is the significance of having this complex number? Okay, so if we proceed further with these equations here, and if we take out, yeah, if we bring out the real values of the permittivity, which is epsilon prime, yeah, from these terms on the right hand side, you're going to have epsilon prime, yeah, and in the bracket we have 1 minus j sigma over omega epsilon prime. Okay, so this particular ratio of sigma over omega epsilon prime is what we call as a loss tangent. Yeah, loss tangent, yeah. Okay, what is loss tangent? So loss tangent basically is a parameter which used to characterize the lossy behavior of the dielectrics. Okay, I repeat again, yeah. Loss tangent is a parameter which is used to characterize the lossy behavior, yeah, the lossy behavior of the dielectrics. Okay, which means that if we have higher loss tangent, yeah, if we have higher loss tangent, yeah, it means that if I can use here loss tangent, if you have higher loss tangent, LT is higher, which means that the dielectric is very lossy. Yeah, the lossy characteristic is very high. Yeah, if you have a small loss tangent, yeah, so the lossy dielectric is lesser. Yeah, means that we're going to have a good dielectrics, which means that the loss is smaller if the loss tangent is small. Okay, so I hope you understand what I meant by this loss tangent. Yeah, so I repeat again, loss tangent is a parameter which is used to quantify or used to show the lossy behavior of the dielectrics. Yeah, so if loss tangent is higher, it means that the dielectric is very lossy. Yeah, and if the loss tangent is smaller, the dielectric is less lossy, which means that what is meant by lossy? So if we have, for instance, yeah, I'm using the analogy of the material, the wave just now. Yeah, if we have, let's say this is your dielectrics, the wave is propagating towards this dielectric. As for examples, we have this wave, for instance, is A naught, yeah, A naught as the amplitude of the wave. So if this medium is lossy, in which we have epsilon equals to epsilon prime plus j epsilon double prime, yeah. So which means that if we have a complex permittivity for dielectric, it means that this dielectric is a lossy dielectric. So the output of the wave, yeah, basically will be having the amplitude which will be smaller. Yeah, so let's say if you have A naught, might be you're going to have A1 here as the output of the wave, in which A1 will be smaller than the A naught. Yeah, because these dielectric will incur losses, the wave, and as such, the output wave will be having smaller amplitude or smaller magnitude as compared to the input wave. Yeah. Okay, so if we go back to loss tangent, yeah. So if based on this loss tangent here, and if you based on the equations here, it can be said that the loss tangent basically will be the ratio between the conduction current and the displacement current, yeah. Because if we base on this equation, yeah, if I can have loss tangent, yeah, okay, loss tangent can also be, normally we use the symbol of tangent of delta, yeah, tangent of delta for loss tangent, which is equals to sigma divided by omega epsilon, yeah. So sigma is conductivity, omega is your frequencies, yeah, frequencies of the signals, yeah, of frequency of the alternating current, whereas permittivity is the real value permittivity. Okay, so if we can have a ratio, yeah, let's say if we go back to the definition of your conduction current JC equals to sigma of E field. Okay, so I just take the amplitude, yeah. So in terms of the amplitude, I'm going to have the JC will be equals to sigma of E, right, the amplitude. Whereas if I consider the JD, which is my displacement current, in terms of the vectors, it will be J omega epsilon of E. So in terms of the magnitude, I'm going to have the JD will be equals to omega epsilon of E field, or just the E, yeah. So based on this, if we can have a ratio between your conduction current and displacement current, okay, we can then have that the ratio between the JC and JD will give us sigma over omega epsilon. So that's why I put it here that the loss tangent in terms of the formulation, it is sigma over omega epsilon, and it is actually equals to the ratio between the conduction current and the displacement current. Okay, and evidently it's shown by this equation that if we have higher conductivity, okay, high conductivity means that the material is lossy, yeah. High conductivity means that the material is lossy. Okay, so that's why we have the ideas when we have a higher loss tangent, the dielectric is said to be very lossy, and we have small loss tangent in which the sigma will be smaller. It means that the dielectric is said to be less lossy. Okay, so this is understandings. I mean, the concept that I want you to understand on the loss tangent concept. Yeah. Okay, so we go back to these ideas in that if you have a loss dielectric or perfect dielectric, because the sigma is zero, so the loss tangent basically will be zero. Okay, so the loss tangent will exist only when we consider the dielectric to be lossy, right? Okay. Okay, this is what can we mimic, yeah, with the concept of capacitor. All right. So for the case of capacitor, we can see that if you are having a loss dielectric as a medium between the capacitor plate, so we are supposed to have only the JD, which is displacement current, to exist in your capacitor, and we have agreed on this. And as such, the symbol for the capacitor will be just a capacitance structure, yeah, a capacitance symbol of C, and the current propagate will be the ID. But when we have a lossy dielectrics, yeah, lossy dielectrics, okay, we believe that, I mean, we have understand from the previous slide that for the case of lossy dielectrics, which is to be exist, exists in the medium between the capacitor plate, there should be two current exists, which are the conduction current, DC, and also the displacement current. Okay, and we have agreed that the conduction current basically will incur loss, yeah, will incur losses to this capacitor. Okay, and as such, the equivalent symbol for this capacitor will be the structure consists of two components, which are resistors, yeah, one resistor, which is in parallel with the capacitor, yeah, in which for the resistor branch, we are going to have a conduction current, yeah, conduction current to pass through, or we can call this as a leakage current. And for the case of a capacitance branch, the current that pass through this capacitance is the displacement current. Okay, so this is the equivalent circuit in comparison between two types of capacitor, which is for the case of perfect dielectric in use and also the lossy dielectric in use. Yeah. So I repeat again, for the case of lossless dielectric, we only have a capacitance. For the case of lossy dielectrics, because of the existence of the conductivity or conduction current, are going to have two components in parallel, which are the resistor and also the capacitor. Okay, I believe that if we consider, yeah, the case of capacitor, for instance, if you are having a perfect dielectrics in this particular case, okay, we have agreed that for the case of capacitor, the current, yeah, the displacement current and also the voltage across the capacitor will be 90 degrees apart, yeah. Yeah, so we have the phasor form, I mean the phasor graph for both the displacement current, the ID, and the voltage to be this form, yeah, in which the current of the capacitor will always lead the voltage by 90 degrees apart. Yeah, the ID stands for the current of the capacitor, and V is the voltage of the capacitor. Okay, this is for the case of perfect dielectric in use. But when we have a lossy dielectric, so if we consider the equations of that set, displacement current, yeah, which is equals to C dV over dt. So we're going to have this as equals to C omega V naught.
Doctor, I think your voice is cutting out.
It shows that conduction current, I can say, or V over R, and that will be equals to V naught sine omega t divided by the R. Yeah, V naught sine omega t divided by R, in which this will be the voltage across divided by the resistor. Okay, and as such, we can see that if for the case of lossy medium, the current will consist both the ID and the IC, and as such, we can have, yeah, the case whereby your current phasor will be look like this, yeah. So that should be the total current, yeah. Total current which consists of the ID and the IC. And if we base on these equations, yeah, we can see that the IC will be in this particular case, in which it is having a same phase with the voltage. Okay, so we can see that that should be your IC. Yeah, so the I total will be a combination of your displacement current ID and also the conduction current IC. Okay, so based on this phasor graph, we can then deduce that this particular angle here will be the angle of loss tangent, yeah, which is the angle of delta. So which gives us the tangent of delta will be equals to, yeah, the IC divided by the ID, the magnitude of it. Okay, so basically that will give us the loss tangent. Yeah, the tangent of this angle, in which the angle meet between the IC and the ID, and tangent of this angle will give us the ratio of the conduction current and the displacement current. Okay, so this is to reflect back what you have learned previously in circuit theory, I believe, yeah. And I just want you to understand relationship, yeah, relationship between what we are learning in these topics of lossy dielectrics with the circuit theory that you have learned in the previous semesters. Okay, so these are relationship between the two. Okay, is there any questions on this topic, on this lossy dielectric before we proceed with the example?
Doctor,
Yes.
for the lossy dielectric, just now the graph, the IT and IC, what is that? Can you explain again?
Okay, the I total here is the combination, because we know that for the case of lossy dielectrics, okay, before that, yeah, for the case of lossless medium, we only have ID, right? Am I right,
Yeah.
Johan? Okay, ID, which is 90 degrees apart from the voltage, absolutely is shown by this equation here, yeah, ID, which is C dV over dt, will be having a cos, whereas the Vt is in sine, so we're going to have 90 degrees apart between the ID and the voltage. But when we are considering the case of lossy medium, we are supposed to have two current now, which are the displacement current ID and also the conduction current IC. Am I right? Wehan? Correct, yeah?
Okay.
We are going to have two
Yes.
currents, right? Conduction and also displacement. Okay, so if you base on the equation itself, yeah, IC, which is V over R, yeah, because IC is the current that passing through the resistor, which is voltage over the resistor. So based on the equation here, we can see that the conduction current IC will be having same phase with the voltage, which is V naught sin omega t divided by R. So as such, if you base on that, we can see that this graph, I mean this line here, which is the I total, basically is the combination of both the conduction current and your displacement current. Because as I mentioned before, in a lossy medium, these two current will exist, yeah, which is the IC and the ID. So I total basically is the combination of the vectors of both IC and the ID, and the IC, as we have agreed just now, should be having same phase with the voltage. That's why we have these IC will be at this location, yeah. The vector for the IC will be at this location, and then from these ideas of IC, we can then deduce that this particular angle will give us the loss tangent angle. Yeah, because we have agreed previously from this equation here that the loss tangent is the ratio between the IC magnitude and the ID magnitude, and it is agreeable to this diagram that the tangent of this angle delta will be a ratio of IC over the ID. Is that clear on my explanation?
Okay. Okay. Thank you.
Okay, all right, okay, well, okay, yeah, hopefully it's clear on this lossy dielectrics. So the things that I want you to understand here is that I want you to understand what is meant by lossy dielectrics, the difference between the lossy dielectrics that we are learning now and the perfect dielectric that we have learned so far. Yeah, because so far we just consider that the dielectric is perfect medium. But for this particular case, we are now getting into the real scenario where we are having a lossy dielectrics where it do have the effect of sigma or the conductivity. And one parameters, I mean, one important parameter related to the lossy dielectric is a loss tangent, which I mentioned just now, that loss tangent is a parameter which is used to quantify, is to measure the lossy behavior of the dielectric, yeah? Yeah, right. Okay, so again, this is how we can use the lossy dielectrics to quantify, to characterize, or to classify the material just by based on loss tangent. Okay, we have agreed that loss tangent will be depending on the sigma. So for the good conductor, basically, we're going to have very high loss tangent, and good conductor is similar to bad conductor, right? Yeah, similar to bad conductor. Sorry, bad dielectric, I apologize. It's similar to bad dielectrics or lossy dielectrics. Sorry for that, yeah, my mistake. It's bad dielectrics. Okay, so back dielectrics means that lossy dielectrics, yeah, lossy dielectrics. So it's you can see that for very high loss tangent, the dielectric will be a very lossy dielectrics, but it will be a good conductor, yeah. And this will be represented by the value of loss tangent, which will be very much higher than 1. Okay, so this is the characteristics for the loss tangent for the case of good conductor. Okay, whereas for the good dielectrics, yeah, which is for the case of bad conductor, okay, we are supposed to have a very small loss tangent. Okay, we have agreed on this issue just now. Yeah, good dielectric will be having very small loss tangent, and this is given by the value of loss tangent, which is very much smaller than 1. So initially for the loss tangent, I mean for the good dielectric, the value is about 0 to the power -3 to 0 to the power -4. Yeah, so this is the typical value for the good dielectrics. Yeah. Right. So this is the things that I want you to understand. Yeah, for the case of lossy dielectrics and how it can be used to quantify the medium of the material, whether the material is it a lossy, whether it's a good conductor or a bad conductor. Yeah, good conductor or good dielectrics in the other way. Okay then, so let's have a look on this example number 5. We are having this example whereby we are given a case of a parallel plate capacitor, yeah, parallel plate capacitor, having a plate area of 1 centimeter squared, and the plates are separated by a distance of 1 millimeter by a dielectric having the following properties at 1 gigahertz. Okay, so we are having these dielectrics, this capacitor, parallel plate capacitor. The plate area is 1 cm squared each. So let's say the area S is 1 centimeter squared. Okay, the plates are separated by a distance of 1 millimeter. Okay, this is 1 millimeter, a distance between the plate, and the dielectrics in between the plates is having these properties in which relative permittivity equals to 2. So I can say that the real values permittivity equals to 2 epsilon naught. Okay, this is the real value of permittivity, yeah. And the sigma, which is the conductivity, is equal to 10 power of -7. Okay, right. So basically, if we base on this, we know that this dielectric is a lossy dielectric, yeah. Because why lossy? Because we have a value of conductivity. So when we have a dielectric with conductivity value, so it is a lossy dielectric, yeah. Okay, so the question is, we need to find the equivalent circuit for this capacitor, okay, and calculate the conduction current. You need to calculate the IC and displacement current, the ID, and subsequently we need to calculate the loss tangent if 1 volt at 1 gigahertz is applied across the capacitor. So basically there are 4 things to be calculated here, or to be obtained here. The first one is your equivalent circuit. Secondly is the conduction current. Third is displacement current, and the fourth is the loss tangent. So 4 things to be calculated or to be obtained. This example. Okay, so for the equivalent circuit, because we have learned in the previous slide that for the case of lossy dielectrics, the capacitor will be actually can be regarded, yeah, as a 2 component. Yeah, so the capacitor will be actually consists of resistor, yeah, and also the capacitor in series. This is for the case of lossy dielectric medium. So we're going to have this equivalent circuit. Okay, so we need to find what is the R, what is the resistor for the capacitor, and what is the capacitance for the for this particular capacitor. So in this particular case, because we are having a parallel plate capacitor problem, yeah, and it is given in this example that the capacitance for parallel plate has been given, and also the resistance for the parallel plate is also given. Yeah, so we can straight away find the resistance and the capacitance based on this equation straight away. Yeah, because we need to find what is R and C. Yeah, and the R and C has been the formulation of R and C for parallel plate structure has been given here. So we can see that the resistor R, yeah, R will be equals to D, which is the distance between the plate, which is 1 millimeter, 1 times 10 power negative 3, yeah, sorry, negative 3 divided by the sigma, which is 10 negative 7, multiply with the area S, which is 1 cm squared, which is 1 times 10 power negative 4. Okay, so that will give us the resistance to be equals to 1 times 10 power of, this is, let me see, yeah, this is negative 11, this is negative 3, so we have power of 8 ohm. Yeah, so that should be your resistance based on these methods of calculation. Yeah, okay. And for the case of the capacitance, you can have the C, yeah, should be equals to epsilon, which is the real value of the permittivity, which is 2 epsilon naught. Okay, and S is the area of the plate, which is 1 times 10 power of negative 4. Okay, and divided by the D, which is 1 times 10 power of negative 3. And if we proceed with this, we're going to have the capacitance value basically will be equals to 0.2 of epsilon naught in farad. Okay, so that should be your capacitance for this particular case, given structures with the plate area of 1 cm squared, the distance of the plate of 1 millimeter, and the properties of the dielectric as given here in this example. Yeah. Okay, so that should be your resistance and capacitance for this equivalent circuit of your capacitor structure. Okay? Right. So let me proceed with the. Is there any questions for this first solution for the equivalent circuit? Any question for this? No, yeah? Okay, hopefully you understand this. Okay, next we're going to calculate the conduction current. Yeah, conduction current. Okay, for the conduction current, I think we have agreed just now that the IC conduction current will be the current passing through this resistor. That should be the IC. Whereas for the capacitance, the current that pass through it will be the ID, which is your displacement current. So IC will be based on the ratio between the voltage across the resistor, okay, voltage across resistor, and based on the given information here in this diagram or in this question, the voltage across the capacitor is 1 volt, so it should be 1, and the resistor R is 1 times 10 power of 8. So based on that, your conduction current will be equals to 1 times 10 of negative 8 ampere. Okay, so that should be your conduction current value, yeah? Right. And then you need to calculate the displacement current. So we have agreed that ID, okay, should be equals to C dV over dt, okay, and in phasor form, we're going to have it as equals to J omega CV, okay, this is the equation for the ID in a phasor form. So we're going to have the ID to be equals to J, omega is the frequency. So we have 1 gigahertz here, so it should be 2 pi of 1 gigahertz. So 2 pi times 10 power of 9 gigahertz, that should be the frequency omega. So C is equals to this value, which is 0.2 epsilon naught, whereas the voltage V is 1 volt given in the questions. So that should be your ID. Okay, I hope that you can please try to solve for the ID, yeah, based on this mathematical solution, yeah, for this J omega C V calculation. Okay, so that should be your displacement current, yeah. Okay, so we have calculated the conduction current, which is based on the resistance value, and we have also calculated the displacement current ID, which is based on this equation of J omega CV. Yeah, right. And finally, is to find the loss tangent. So I think since we have obtained the IC and ID, we can straight away find the loss tangent. So we know that the loss tangent basically will be the ratio between the amplitude of IC and also the ID. Okay, that should be the loss tangent value. and IC is 1 times 10 power of negative 8 as calculated here, and need to find out what should be the amplitude for this ID, which is supposedly 2 pi times 10 power of 9, yeah, multiply with the multiply with your C, which is 0.2 epsilon naught, and the volt, which is 1. Okay, so please calculate these values. Yeah, so that should be the loss tangent of your material. Yeah, loss of material at this particular frequency of 1 gigahertz. Okay. Any questions related to this example number 5 on calculation of loss tangent, calculation of conduction current and displacement current? Okay, I hope it's clear, yeah? This is example number 5. Okay, so we can now proceed with example number 6, yeah? Example number 6. Okay, so this is a sample of past year's question. We are having about the same problems. Again, we are related to the capacitor structure. So normally for displacement current, for the case of Lossy Dielectrics, most of the time we will try to relate the problem to the capacitor structure. Most of the time, yeah. Okay, most of the time. So you can predict or you can expect this kind of capacitors problem will be tested, yeah, in your final examination, yeah, because as I mentioned before, for Faraday's law, yeah, Faraday's law, it will not be tested in your final examination. That's why I gave you this Faraday's law as the assignment topics. But for displacement current and Lossy Dielectrics, so that will be tested. Yeah, that will be tested in your final examination. So you need to understand that clearly. Yeah, yeah, the concept of displacement current and Lossy Dielectrics. Yeah. Okay, so we go back to this example number 6. Again, we are referring to the capacitor problem, which we are having a parabolic circular, yeah, circular plates of radius A. Okay, so it means that should be your capacitor structure, which is circular in terms of the cross section of the plate, and the dielectric between the plates is imperfect. Okay, said to be imperfect with parameters epsilon, sigma, and mu naught. Yeah, so imperfect means that this dielectric here is a lossy dielectrics. So under the circumstances, obtain the magnetic field intensity vector in the dielectrics. So we need to find what should be the H field inside the dielectrics. Okay, yeah, so the question is somehow different as what we have based on the previous example. Yeah, you need to find the H field inside the dielectrics. Okay, so we know that the voltage applied across the capacitor is given to be these values. The Vt is here, so it is given to be V0 cos omega t, yeah, which means that the voltage is a time bearing, yeah, which is the AC voltage, yeah, AC voltage. Okay, so we need to find what should be your H field inside the dielectrics. Okay, so basically there should be two methods to solve this equation. The first one is by using the Maxwell equation. Okay, and secondly is by using the basic Ampere circuital law. Yeah, I'm going to adopt the first method, which is by using the Maxwell's equation. Okay, so you know that we need to find the H field, yeah, inside this medium. Yeah, inside this medium, which is inside dielectric. And from what we have learned before, since we have the case, the H field, yeah, to find the H field in a lossy medium, we can say that the Maxwell equation related to this particular problem will be the curl of H shall be equals to the J plus dd over the dt. Okay, yeah, so that should be the case, yeah, that should be the equation to be used, because in this particular case, we are having lossy medium, yeah, or lossy dielectrics, which consists of conduction current and also displacement current that propagate inside these dielectrics. Okay, so based on that, we can say that the J, yeah, should be equal to sigma of E field. Okay, in which we assume that the E field is directed due to the V, yeah, because we have learned before that the V and E is interrelated. V equals to negative integrations of E dot dl. Okay, so if we base on this diagram, because the distance between the plate is D, so we can see that the V will be equals to the E times D, and as such, we can say that the E shall be equals to the V divided by D. Yeah, so this will be a very simple relationship between the electric field and also the voltage. Yeah. And as such, we can say that this equation of the J, or the conduction current, shall be now returned to be, yeah, I just use the amplitude, yeah. So the J amplitude, this will be equals to sigma. The E will be equals to V over D, which will be Vt over D, and that will be equals to sigma V naught, yeah, V naught cosine of omega t divided by the D. So that should be the J, yeah, the amplitude of the J. Okay, the same things applied for your displacement current. Yeah, so we have dD over dt. So we can write this as epsilon of dE over dt. Okay, and if I consider just the magnitude, so this is the JD, yeah, JD as dd over dt. So in terms of magnitude, I can just have it as equals to epsilon dE over the dt. And in terms of the V, yeah, because we have this relationship between the E and V, so we have this as equals to epsilon divided by D of dVt over the dt. So when we differentiate the Vt with regard to time, we are supposed to get epsilon omega V naught divided by D of sine, I shall put negative sign here, of sine omega t. So that should be the amplitude of JD, yeah? Yeah? Okay, so we can see that the J and the JD is having different direction. Yeah, J is positive and JD is negative, yeah, different direction. Yeah, because of the negative sign of the sine of the cosine just now, we will differentiate, we're going to have negative sign. That, and if you proceed with this, you're going to have, okay, I'm referring to this slide, new slide, yeah, curl of H shall be equals to, we go back to the equation here, yeah, JC plus JD. So I just consider magnitude just now for the right hand side. So we have the curl of H shall be equals to, okay, sigma V naught cosine omega t divided by D. Am I right? Yeah, correct. And minus epsilon omega, okay, epsilon omega V naught divided by D sine omega t. Okay, this is the case. Okay, so we know that the current J and JD, yeah, if we assume that this is Z direction, yeah, Z direction. So we can see that this particular current, yeah, this particular current will be having a direction of Z. Yeah, because if you base on this, if you base on this equation and based on the direction of the E field, okay, because we know that V is actually exists between the plates, yeah, between the plates. So as such, you can see that the E field will be actually in the Z direction, and due to that, we can see that the current will also be in the Z direction. Okay, so we need to evaluate the curl of H here, and the curl of H has been given here in this equation. Yeah, so we have the curl of H to be in the R direction. It also exists in the phi direction and also in the Z direction. Yeah, so this is the basic equation for the curl of H. But since we have agreed that from the equations here that the curl of H will only be in the Z direction, because from this argument just now, yeah, because the current will only be in the Z direction. So due to that, we can only consider this term to exist. So it means that these terms of R direction and the terms of the phi direction can be cancelled out. Yeah, so you only consider this effect, the component of the Z direction. So for that, we're going to have the left hand side to be 1 over R. If you base on these equations here, it will be 1 over R, D over dr, okay, D over dr, R of H phi, okay, minus dhr over d phi, equals to sigma V naught cosine omega t divided by d minus epsilon omega V naught over d sine omega t. Okay, this is the case, yeah? Right. For this particular case, yeah, we know that, yeah, if I can go back to this particular, I can say your capacitor, yeah, we have agreed that your current is in the z direction. Yeah, current is z direction. So by using the right hand rule, yeah, by using the right hand rule, we can see that your thumb will be the current direction and the rest of the fingers will be the field direction. So as such, we can say that your field will be in this field direction, correct? Will be in the field direction. Yeah, because the current is in the z direction. This is based on the right hand rule, yeah? For right hand rule, I think all of you understand that the thumb will give us the direction of the current. The rest of the fingers will give us the field direction. The field direction, yeah? So as such, we can say that based on that argument, your field, your magnetic field will only be in the field direction because of that argument. Yeah. So from this left hand side, the terms of HR can then be not, because we have agreed that the H field will only be in the field direction based on this argument of the right hand rule. Okay, so for this, we can proceed with this integration straight away. So we're going to have R of HV shall be equals to R dr integration. Okay, and then we're going to have sigma V naught cos omega t divided by d minus epsilon omega V naught divided by d sine omega t, because all of these are constant, so we only integrate with respect to r. Okay, so we just take the value of r from 0 to r, yeah, because we consider the region of r to be any position inside the capacitor plate, yeah. So r will be a radius. So let's say this is the center of the capacitor plate. So r will be the radius of r, yeah. Should be the r. Although we are given that the radius is a for the capacitor plate, but we need to find the h at any position inside the capacitor. So we just put the range of r to be r only, yeah, in which this equation of HV will be valid for any position inside the capacitor. So for this, when we proceed, we're going to have the value of HV. If I bring the r to the right hand side, I'm going to have it as equals to r divided by 2 of sigma V naught cosine omega t divided by d minus epsilon omega V naught divided by d sine of omega t. So that should be my HV. And for that, we're going to have my H vector will be HV in the direction of feet in ampere per meter. Okay, so that should be R, yeah? R divided by 2. So this means this is your H field, yeah, for any position of R, whereas R, the radius must always less than A, which is any position inside the capacitor, yeah, inside the capacitor. Okay, is that clear on these solutions for the H field inside the capacitor?
Doctor, may I know for the current, is it necessary compulsory we put the z direction is in?
Compulsory to put z. What mean by that?
If you want to do it in not in z direction, is it okay?
Okay, in this particular case, yeah, because we have agreed, yeah, normally we assume that the capacitor, the arrangement of it should be in this direction of z. So which means it makes our calculation to be easier. Okay, so that's the reason why. Okay. So all the time we assume that z to be in the z direction. So that's why we're having this particular case, yeah.
And may I know for the RH naught, for the RH naught is, where is the term to get the RH naught?
RH naught, where is RH naught? This is R, bukan, not RH not, this is HV.
Ah,
The V
HV,
direction.
sorry.
The HV.
HV.
Okay, all right. Why? What's the question then?
How to get the RHV?
Okay, because what I did here, because I straight away jump to here, yeah, because basically, if we proceed with the R, okay, you bring the R to the right hand side and you need to integrate, right? You need to do integration. So when you do integration, we left only with the RHV on the left hand side. This will be integrated, am I right?
Integrated?
Integrated, okay.
Oh.
Okay, 1 over R, D over dr, RHV, let's say I can put A here, yeah? So we're going to have D over dr, sorry, put that, okay. Okay, so I'm going to have R of HV equals to AR dr integrated, am I right?
Oh, yes.
Okay. So hopefully it's clear, yeah? All right, good.
Thank you.
Okay, thank you. So this is the first method. I think it's worth to proceed with the second method. Hopefully we still have time for that. Yeah, we still have time for that. Okay, let me proceed the second method, which is to find the heat field inside the capacitor. Okay, so this I'm going to use the ampere-second law, yeah? So we have this diagram of the capacitor itself. We are having this as the A, the radius. So in between, we have the dielectric of permittivity epsilon, sigma as the conductivity, and also the mu naught as the permeability. Okay, so what I did here is that I'm going to use the ampere-second law to find the H field inside this dielectric, in which what I'm going to use is I'm going to apply the ampere-second law, the ACL. So to find the ACL, or to use the ACL, what I have to do is that I have to sketch the Amperian loop first. Okay, so that should be an Amperian loop, which is a circular structure, Amperian loop. Okay, and having the radius of R. Okay, so I'm going to find out what should be the H field that is propagated, that exists inside this capacitor or inside the dielectric. So from the ampere-second law, okay, so from the ACL, we are having the H dot dl, through sub of H dot dl equals to the I enclosed, right? I enclosed. Okay, so for this particular case, since we know that for your capacitor, since we have a lossy dielectrics, your I enclosed will consist of two currents, in which we're going to have contribution from the JC and also contribution from the JD, right? So we're going to have two currents here. So what we can do now is that we're going to include these two currents together in the I enclosed calculation. So we're going to have the HV of 2 pi r. This is for the integration on the loop itself. And I enclosed, I can write here as integrations of JC dot ds, yeah, and plus integrations of JD dot ds, yeah, because this is a calculation of the enclosed current. Yeah, enclosed current, it will be JC dot ds and JD dot ds. So we have agreed there, yeah, we have agreed before that the I will be equals to integrations of J dot ds, yeah. This is the equation that relates the conduction current, the current density J and the current itself, the I, yeah. So that's why I'm using I enclosed is the, this will be the IC and this will be the ID, yeah. This is J, yeah, JD dot ds. Okay, so from here, we're going to have HV will be equals to 1 over 2 pi r. Okay, so if we proceed with this integration, the JC dot ds, yeah, will be the current that passing through this particular cross section of your Amperian loop. And since we know that the loop is having a radius of r, so integration of ds, if I can write here, yeah, integration of ds for this both terms here will be equals to pi r squared, yeah, because we are having a circular plate structure. So the integration of the ds for these two integrations terms here will be equals to pi r squared. So for this, you're going to have the JC dot ds integration will be equals to JC multiplied with pi r squared. And similarly, for the second terms of the integration, it will be JD multiplied with pi r squared. Yeah, so that will be your current that is said to pass through or said to exist or said to enclose inside the Amperian loop of radius r. Okay, so from here we're going to apply the JC that we have used in the previous method number 1. Just to repeat again, so JC will be sigma of E, which will be sigma multiply with VT divided by D, okay, which will give us sigma over D V naught cosine omega t. So we're going to have it as 1 over 2 pi r, okay, sigma over D V naught cos omega t plus the JD, yeah, will be equals to let me see, yeah, so that should be equals to, if we base from the previous slide, just now you're having it as equals to this terms will be this one, yeah, sorry for that. So that should be equals to negative omega epsilon V naught divided by D, am I right? Yeah, sine omega t. Okay, so just remember, yeah, this is obtained from this equation, differentiation of dd over dt, yeah, that will let us find the jd then, yeah. So we need to substitute this in the equations here. So we have negative of omega epsilon v naught over d sine omega t multiplied with pi r squared, all of it. Okay, so we can cancel out few terms here, pi r squared, yeah. We can cancel out the pi, we can cancel out the r, so we left only with what? We have only with r over 2 sigma over d v naught cosine omega t minus omega epsilon v naught over d sine omega t. So that should be, yeah, that should be your h phi, yeah, h phi, and from here we can find the h vector, which will be h phi direction of phi, and in which it's believed, I mean, it's clearly shown that from here that the h field will be depending, I mean, the h field that we have calculated here is the h field at any position of radius r from the center of the capacitor. So basically the answer that we obtained from the second method should be similar to the answer with this first method that we did just now. Okay, is that clear on this method of calculation for the H field? Yeah, so we have two alternatives here, whether you want to use the Ampere's-Circuitor law, yeah, based on what we have done previously, or you can also base on the method of Maxwell's equation.